let's go to the topic of the course, digital engineering preliminaries. So we talked about this, the continual improvement workflow for new construction. You have the digital engineering model. So whatever you plan initially, you have that. You need to be able to transfer that to the real world and build this, basically what we call realize it. You need some intermediary technology, and not just you are using it on every construction project, some intermediary technology to basically improve this amount of communication from whatever you've planned here to whatever it is in reality. Then you would have to monitor it and see what basically the status of the reality is. If there are any deviations, for instance, in this case, you remember we talked about the competition pool there. That needs to be identified and reported. And if there are any deviations, we go back to the digital and then we try to revise the plan and revise the whole design accordingly. Okay. So not only do we perform this individually, which I'm going to be talking about it in every step, you also are going to do it as a whole in a project so that we can improve it as time goes by. And the earlier we identify these deviations, we talked about it, the better. Why? Because we have more opportunities to be able to improve it if we need to. Right? Okay, so this is what I call the digital engineering design, the constructed facility, and the performance assessment. Okay. And today we're going to be talking about the digital engineering design. Okay, so NASA has a definition of this, which is basically, again, a cyclical process, especially when you're dealing with something new. If you're dealing with something that you're going to be improving, it basically has to go through to this area. So you already have this, you have some experimentation, you improve, and then you go and start the cycle from somewhere else, right? That's the whole idea. Again, with the continual improvement process that I talked about, if you already have a constructed facility, you start from the monitoring and then you go back and improve it, right? So that's the whole idea. With these cyclical processes, dependent upon where you're starting. If it's completely from scratch, then obviously you have to identify those requirements there. So you ask about that from your client. You have to imagine, so you have some solutions that you have to come up with that you know that could potentially satisfy these constraints and these requirements. Then you're going to be planning and then identifying what it is. The good news about this is that the majority of these, at least in terms of the digital engineering part, can be carried out digitally as long as we have the proper responses of what we expect would happen in reality in terms of its analysis with respect to engineering. What do I mean by that? That means that how do we perform structural analysis on a computer? We already know that, let's say, the response of a particular material is in a particular way, either linear, if we're looking at the elastic region, or something else. By means of that, you would be able to know if you have whatever boundary condition you have and whatever load you're going to apply to it is going to have a particular displacement because of that. What that means is that we need to know this. If we don't know this, we have to create and experiment on it, like a real experiment, or at least put parts of it that we do not know. Hello? Parts of it that we do not know, and experiment on it and know exactly what it is so that we can then simulate it. That's the whole idea. And then we improve on it. So for instance, if there's a cantilever there that is going to displace more than what we require for the quality and the safety standards, then we put some sort of temporary or some sort of basically additional support there, and then that would be basically your design. And this goes forward and forward until all of these constraints are met. Okay. So it's a typical optimization problem, right? If we have, again, talking about what we talked about last session, if we have some sort of initial design, we start from here, and then we try to improve it because we now know the problem, we know the constraints, and we know the boundary conditions. Once we have all of that, we would be able to utilize some sort of tool. Nowadays, with respect to AI, we would be able to optimize this and improve it, and then receive some solutions that satisfy our constraints even better than the original solution that we have. But it requires a good formulation of the problem, and our simulation needs to be accurate. meaning that whatever I'm simulating in terms of the responses, for instance, in terms of the structure, needs to actually have a good, basically a good agreement with what actually happens in reality. That's the whole idea. Okay, so building information modeling, where does this come into play? This comes into play when we actually want to add whatever information we want. And nowadays, with the aid of basically information systems and information modeling in general, we have the opportunity to basically model all of this information as a process inside of one, ideally 3D model, that we would be able to utilize it for various different types of aspects. And we can have it as a unified model. And this is what's important here. We already talked about how computational methods in engineering has been carried out, and it has been carried out for ages. We want to have this as a unified model so that everyone and every party can actually provide all of their information into one system, one environment, one model, and all of the engineering can be carried out on that particular model, okay? So what is building information modeling? It's the combination or the linkage of non-graphical information, technical specification, that means material. So let's say one of the differences between a CAD and, let's say, if you want to add BIM to it, would be that in a CAD, basically a CAD element does not have information related to, let's say, its material properties. That by itself cannot be utilized for any type of engineering without adding that type of information to it, right? It would only be, let's say, geometry. So you have non-graphical information like technical specifications. You can get basically schedule inside of it. That's sometimes called 4D modeling. And basically, you add an extra dimension of time to it as well, so that the activity sequencing and everything else is there. You can provide cost information. This is sometimes called 5D modeling. Again, these are just words and definitions that are there. But really, what these provide for the most part in the industry are simulations. And we talk about that as well. Or you can have risk assessment and risk analysis, or any information about potential risks that could occur for particular activities. We all add these and link these to the graphical information. And where the simulation versus actual building information modeling happens, or intelligent building information modeling happens, that this is going to be a two-way process. So if it's just one way, that's just a simulation. That means that, for instance, I could simulate how this particular construction had been carried out, okay? But if any of my requirement changes, I need to, again, do this completely manually. There's no intelligence built in the system that can actually go back and redesign or re-improve all of the other aspects and other elements and other activities that can actually impact this one, whatever change that is carried out, okay? And that's the whole idea, and that's where, in terms of our industry, we're still not there. We are barely getting this part of it, okay? So then the other side is going to come, and it requires quite a bit of research as well for us to be able to effectively utilizing. We can do it more or less in SOL. So let's say in structural engineering and mechanical, you would be able to do it more in discipline specific, but as a whole, this is where one of those important aspects of research is. How can we build intelligence into the information that we provide so that these linkage between the information can actually provide us with some opportunity for decision support later on, okay? And whatever information we have, we share it in a common data environment in the spirit of transparency so that everyone knows what the requirements of this particular, let's say, building, particular construction is, right? So where can this be utilized? Then once this is utilized, you can perform various different types of analysis on top of it. You can utilize the same design, the same model, and you would be able to perform, let's say, wind analysis. On the same one, you would be able to perform structural analysis. So you can basically remove all of the elements that are not necessary, or could let's say, minimize your opportunity to be able to perform the structural analysis and only get basically the skeleton of the structure. Or you can perform wind solar analysis that we talked about as well, or any other types of analysis. The whole idea is that once we have this information modeled properly and correctly, and I'll give an example of how it could be modeled incorrectly, because it has to be interoperable with whatever software we're using for analysis. and it has to be understandable for other software as well, right? Whatever we have in our mind that what it needs to happen, it needs to be modeled effectively. An example of this, for instance, is this beautiful model of this building that I actually monitored as a part of my PhD as well. I did this in terms of the comparison between the BIM and the point cloud and identifying the displacement of particular cantilever, large cantilever beams. And this model was basically the stakeholder client-ready final model that they provided. Once you utilize it for structural design, even inside of Revit, it does not work. Why? Boundary conditions were not set there. Nothing about it. And this is the structural model of this particular. And this is a very, very important multi-million dollar project that was carried out in Calgary. So what does this mean? What this means that intention matters. Similar to what we talked about last session, you can collect point clouds. The technology for laser scanners has been around for generations, right? Well, not generations, but at least for the past 20 years, you've had point clouds that you can acquire very accurately from any construction projects. Whatever had been carried out was basically just there on a side. One part of it was that it was challenging to be able to process this because of the big data nature of it. But that aside, still to this day, it's not being effectively utilized. What does this mean? That means that whatever we're modeling, whatever we're carrying out needs to have some intention behind it. You cannot basically just model and say, oh, this is pretty and we've done BIM here. No, you've not done BIM if it's not actually solving the problem for us. If it's not actually being utilized for other parts of it, that means that you're doing a sole BIM. Basically, this discipline is going to do BIM, however way they want, and the other one is going to do it however way they want, and hopefully they could come to some agreement at some point, and then we call it BIM. That's not what we want. What we want is some unified model, unified area that you would be able to utilize all of these together. No problems, no interoperability issues. And how we can get there is so that we know what the requirements are and why we're basically doing this. Okay? So needless to say that this was not carried out. We have someone joining us online. Interesting. So yes, so requirements is key. That's what this area is. Another example, interoperability. So now this is getting a bit better nowadays because we now have opportunities with, let's say, if you have any type of model with a particular type of, let's say, file format, let's say Revit, you want to convert it into STL or you want to convert it into any other, you might get some issues. Nowadays, Revit is doing much better in this STL, let's say, conversion. STL, have you guys ever heard of STL? STL is stereolithography file, which basically triangulates your whole basically model into a set of meshes. This is going to be utilized for finite element analysis and various different types of engineering analysis later on. Or SAT, which more or less does the same thing, but for instance, in this case, the model was effective for that. Nowadays, it's a bit better. Why I'm saying this? Because one of the major contributions of, let's say, Building Smart as a basic organization. Have you guys, by the way, heard of Building Smart? Yes, okay. So you guys know more or less what it is, and I guess that you know what IFC is. Yes. IFC is Issue Foundation Class. It's an interoperable model. In a crude way, we can think about it as a PDF for sharing and opening and reading BIM information using any software. So Revit can read an IFC model, Synchro can read it, and various different types of other, let's say, BIM-based tools can actually read it so that you don't have too much of an issue with the interoperability there. Because previously, the opportunity for you to be able to read Revit in another software was almost impossible, right? This by itself is important, because then the idea of competition, the idea of that also comes into play. That means that Autodesk would rather you as a company use all of their products together, right? But then if they're doing that, they have to have a full comprehensive solution, right? And that has been what the real challenge is. If we're going to be using all of the software, then it has to be comprehensive, right? And it has to solve it. Wasn't possible. We have other alternatives and other options right now. So you need some sort of opportunity to be able to bridge this gap so that you can utilize this information as a large team that even so, it might be just that they're more, let's say, trained in Revit, another one is more trained in Synchro, and so on and so forth, right? Yeah. So this is something to also keep in mind. Once you solve all of these, now you can go into the nitty-gritties of these. And these need to be solved early on in the project, even in the feasibility. If you're doing a BIM-based project and you're performing the planning and you're doing the information modeling, you need to know ahead of time in the very beginning, what parts of this are you going to do BIM? Which parts of it are you going to be performing engineering analysis on that so that you can have all of the constraints that you need for the problem early on? And what softwares are you going to be using? Are they interoperable or not? And not just that they're interoperable together, are they even interoperable with your facility management software at the end as well? Is your facility management software going to be utilizing this or not? You know, we had some problems, I think this was in 2017, with many of this BIM-based, let's say, projects that had these sole BIM models that, you know, some of them were very detailed and very good. The facility management software that they had, and they wanted to use a particular version of ArchiCAD, for instance, was not able to read any of these effectively. They needed to be remodeled again. Now, it's possible to do that. It's just waste, right? We don't want to do that. We don't want to have a situation where all of the information that we've plugged into it once, we plug it in every time, you know? So for instance, an example of that with the structural parts, we've already done the structural. It's professionally done. Why not have an intention behind it? Why not have all of the information that we need at the basically end of this early on, so that the waste in terms of what we're plugging in, what information we're adding, is going to be minimized as much as possible. And that's also very important, right? So that's why intention is important. That's why it needs to be carried out and thought through from the very beginning, right? Okay, BIM-based digital engineering. I gave a very simple way of, okay, we start from visual geometric programming. We add whatever information we want, however way we want, again, with intention of what we want to use it for at the end. We then have the ability for us to perform various different types of engineering analysis. Now, if it does not meet the requirements that were set from the very beginning for each and every one of these, let's say your displacement is not however way it's supposed to be, then it has to go back and everything else has to be improved and changed as well. And this is what's important. What I don't like, or at least not that I don't like it, I think is inefficient, is if we have a situation where only the structural engineer is doing this and everything else is not changing at the same time. I'm of the opinion we now have the opportunity to model all of these together. It's going to be challenging, it's going to be a bit messy, but we can do it. And actually there's systematic ways of us being able to do it for, let's say, building construction, for bridges, and etc. By design, we can actually do this. We can actually start from very, very good, let's say, initial design and initial, let's say, perspectives, and then work our way up to see how it is, so that we don't just change, let's say, the structural part, but we again separately change the let's say mechanical parts or the electrical part. We want to do this all simultaneously. That's where real information modeling and linkage between these items could actually come into play. My argument there, I'm going to be talking about information modeling. One of the examples I'm going to say, if we can model these and if we have some information, we can perform clash detection. I think if we do it properly, we don't even need to look for clash detection. But unfortunately, we're not there, right? Software capabilities, various different aspects. However, this is something to just keep in mind, that we don't want to just be confined to one area. We want to really try to bridge these gaps and really want to utilize this digital technology and digital infrastructure that we have that previously we did not have, and the computation power that we have with cloud-based computers and various different aspects. Okay, so visual geometric programming. Typical ways that we would be able to do this is with softwares or with, which used to be open source softwares like Dynamo and Grasshopper. So Dynamo got acquired by Revit. I think you can still find it as an open source, if I'm not mistaken. If not, you would be able to access it through Revit, which thankfully, because you're a student, you have that opportunity to do that. Grasshopper now belongs to Rhino, and unfortunately, you can only get a 90-day subscription as a trial to be able to do that. Previously, it used to be for free, and Grasshopper is a bit more, let's say, professional in some of those aspects. It's some functions are built in a bit better, and a lot of, let's say, engineering analysis that are a bit outside of the norm. Typically, they utilize Grasshopper, but we're going to be talking about Dynamo because it's just free, and that's what we have. But I would still recommend you to take a look at that. Once you have this, you get these nice boxes with these, links that are between them, and based on that, you can formulate your problem as a parametric design. Once you know what the linkage between different elements and different activities and different, let's say, objects are going to be, then you have the opportunity to optimize them, because you can optimize it in a holistic way once you know the linkage between them. That's the whole idea of this, right? Yeah. And we're going to go through some of the examples as well. So how do you install and download Dynamo? Well, or these tools. One way is by means of Dynamo Sandbox. At least till last year, this worked. You're going to be my guinea pigs to know whether this works this year as well or not. If it doesn't work, then next year I will make sure I'll tell the students. So, but any which way, you have that access through Dynamo Revit. Okay. The other one is Grasshopper with Rhino 3D, and this by itself, at least last year till 7, you needed an access, but you can get the 90-day access for education for free. You would just need to make a request, so it's not necessarily as streamlined as what you get with Revit, but you get the gist of it. You get 90 days, and if you basically download it within the next couple of weeks, you more or less have it till at least the end of January or something like that. So you would have it for the majority of the time that you would need it for this course, at least. Okay. So with that being said, I take that everyone has installed Revit. Yeah? No? Okay. You have about 10 minutes to figure out how to install Dynamo or Revit. I think you can do Dynamo as well. You can go through Dynamo Sandbox, and then you're going to be completing this activity here together with one more person. But I would like both of you to know how it is, and this is, I think you can do it. So after I give you about 10-15 minutes to complete this, you need to create basically a grid of cylinders where every aspect of this can change. So the distance between these cylinders would change, so the grid distances would change. The number of grids would change. The height of the cylinder would change, and the radius of the cylinder would change.